These notes cover sums, in particular notation, the arithmetic sum, the geometric sum, and also one example of an induction using sums. So let's first look at notation. So this is a sum symbol, so this would be the sum from I going to from 0 to n to I, so that is a sum symbol, and I is index variable, and then we have the range from 0 to n. So this would be 2 times 0, because we start with 0, plus 2 times 1, plus 2 times 2, up to 2 times n. Just another example, this would be the sum going from 2 to 5 I squared, so that would be 2 squared plus 3 squared plus 4 squared plus 5 squared. This would be the sum of with the index variable j, starting at 1, going up to log n. So if I write log n here, more formally, that should be log n rounded down, and this is shown by these brackets, which indicates a floor function. The brackets on top would be the ceiling, so rounding up, but this is rounding down. And if I, for instance, have the sum, if I just sum up ones, then what I get is simply the number of terms. So I get 1 plus 1 plus 1, in this case log n times, or log n times rounded down, and that is then simply 1 times log n, so that's log n. Double sums occur often in the context of nested loops. So this would be a double sum where I have first a sum over I and then a sum over j. Note that the sum over j, so the range is from 1 to I, and in this example I'm summing over 1, so this inner sum sums 1 I times, so this could be rewritten as the sum over I and then I, and this then evaluates to n times n plus 1 half. So this is actually the arithmetic series. Let's have a closer look at that, because that occurs quite frequently in the context of for loops, for instance. So what we just seen is our arithmetic series, so the sum over I, and as I said, that is n times n plus 1 half, and in terms of growth, so we can rewrite this as n squared half plus n half. So the growth rate is n squared. So in terms of algorithms, if this determines the running time of an algorithm, so such maybe I have a double for loop which results in this running time, then the running time is n squared, which indicates quadratic growth. Just how can we see that the sum is actually that sum? So formally we would prove that by induction, but just to illustrate this with a couple of small examples. So if I have the sum 1 plus 2 up to 6, so if I sum up the first and the last term, and the second and the next to last term, and so on, so 3 plus 4 is 7, 2 plus 5 is 7, 1 plus 6 is 7. Overall I have 7 3 times, which is actually 7 times 6 halves, which is exactly this n times n plus 1 half. This also works if we sum up to an odd term. So now I could have sum up 1 and 5, 2 and 4. 3 is left, 3 is in this case 6 half. So I have 6 plus 6 plus 6 half, so that's actually again n times n plus 1 half. As I said, in an algorithmic setting, double for loops, this occurs in double for loops if I have a constant time operation inside. So that could be something like this. So I have a for loop going over I, then j, but j goes up to I, and then I do something like here printing, and then that algorithm would have quadratic running time. Another important sum is a geometric sum, a geometric series. So that is a sum over a to the I, where a is some number. For instance, if a is 2 and n is 4, I get the sum I from 0 to 4, 2 to the I, which is 2 to the 0, which is 1, plus 2, plus 4, plus 8, plus 16. This is actually 31. And 31 again is actually 2 to the 5. So the last term was 2 to the 4. 31 is 2 to the 5 minus 1, which is not a surprise, because as a general formula, as long as a is not 1, we get that the geometric sum up to n is a to the n plus 1 minus 1 divided by a minus 1. So the example of 2, this is of a is 2 and n is 4, this would be a to the 5 minus 1, 2 to the 5 minus 1, which is exactly what we had, divided by 2 minus 1, 2 minus 1 is 1. In terms of growth rate, so if a is small, so in particular a is smaller than 1, then this sum is bounded, so it's constant, and otherwise it's essentially grows like the last, as fast as the last term. So the growth rate essentially is a to the n. So in the example of 2 to the, if a is 2, then the growth rate with increasing n is of order 2 to the n. An example for a small growth rate, so if a for instance is 1/2, if I plug in 1/2 into all of this, so it's the sum 1 plus 1/2 plus 1/4 and so on. If you look at this first sum, it gives us 1, then if I add 1/2, I add up to 1.5, then I get 1.75 and so on, and we always stay below 2, so this actually converges to 2, but in particular stays below 2. Geometric sums in the algorithmic analysis occur in particular when we are analyzing recursion trees, which we will see later. Okay, so let's use this opportunity to do a proof by induction. So let's prove the geometric series by induction. So we do a proof by induction. We need a base case. The base case here, our sum starts at I being 0. So it starts at the base case is n is 0, then we only have one term, namely a to the 0, which is 1, which is the same as a to the 1 minus 1 divided by a to the 1 minus 1, so a to the n plus 1, if n is 0 is a to the 1, a to the 1 minus 1, and I divide by a minus 1, a is again a to the 1 minus 1, as long as a is not 1. So both sides, the left hand side and the right hand side of what I want to equate, are the same for the base case. Now the induction hypothesis, we assume that this equality holds for some n, and now we want to prove it for n plus 1 in the induction step. And now we use a standard trick that we split off the first the last term, so we have the sum up to n plus 1, for which we now want to prove that it is and then if you plug n plus 1 on the right hand side, you get a to the n plus 1 plus 1, so a to the n plus 2 and so on. So we split off the last term, which is a to the n plus 1. The remaining part is something we already know something about. It's a sum I goes from 0 to n, a to the I, which by induction hypothesis we assume is a to the n plus 1 minus 1 divided by a minus 1. So we started with the left hand side, we wanted to get the right hand side. We don't quite have the right hand side yet, because the right hand side should be a to the n plus 2 minus 1 divided by a minus 1. To get this, we first make sure that all of our terms have the same denominator. So I want to have also for a to the n plus 1 the denominator a minus 1. So I divide by a minus 1, I need to multiply by a minus 1 a to the n plus 1 multiplied with a minus 1 is a times a to the n plus 1, which is a to the n plus 2, minus 1 times a to the n plus 1, which is simply minus a to the n plus 1. So this first term is a to the n plus 2 minus a to the n plus 1 divided by a minus 1. What we now see is that I have a plus a to the n plus 1 and minus a to the n plus 1, so those cancel. And what remains is a to the n plus 2 minus 1 divided by a minus 1, which is exactly what we wanted to have, because if you on both sides plug in n plus 1 instead of n, then this is exactly what we should get. So the induction hypothesis holds again for n plus 1, and we're done with our induction proof. So and this was a kind of a quick overview of sums, so the most important sums for this course.